Welcome back everyone to Advanced NLP. Today we dive into one of the most powerful tools in modern language processing, embeddings. This is not really just about how the words are represented as numbers. It's about how we unlock semantic understanding, analyze meaning, and power real-world applications like search engines, chatbots, and even more. I'm Ahmed. I'm co-lecturing this course together with Professor Dr. Georg Groh and the social computing colleagues. And in this session, we will build a bit on what you've learned in NLP 1, a bit of the content in NLP 2, but we're gonna go deeper into types of embeddings, how we analyze them, and what can actually we do with them. So, for example, if I tell you the bat flew across the cave and he swung the bat hard at the ball, you understand both perfectly. But how can a machine distinguish between the two meanings of bat? Embeddings is key. So let me walk you through what we'll cover today. First, we're gonna quickly go into what you have learned in NLP 1 about meaning and word vectors. Then we're gonna talk about different types of embeddings, what they are, how we train them, and why they matter. Next, we take a look at how we analyze embeddings, what kind of information they hold, and how we can understand what the model has learned. Finally, we'll focus on how embeddings are used, and we're gonna get a couple of applications on that one. Let's start by going back to something familiar from NLP 1, lexical semantics, which is just the study of word meanings. First, we look at how words are related. Words that belong to the same category often show up together. This is called a semantic field. For example, if we say mammals, we're usually talking about things like bats, rodents, primates, and which are all semantically related. Second, words that can also have different meanings or senses. A great example is the word bat. If you look it up in WordNet, you will find two different meanings. One is bat, the animal, a small flying mammal that uses echolocation. The other is bat, that object, a stick you hit in sport like baseball or cricket or whatsoever. So same word, totally different meanings. And that's a big challenge for machines trying to understand language. But apparently that's also very interesting for us. Next, there are the relations between word meanings. For example, synonyms are words with similar meanings, like big, large. Antonyms are opposites, like hot, cold. And we also talk about hyponyms and hypernyms. For example, a rose is a type of flower. So rose is a hyponym of flower. And finally, we look also at the connotation of words. This means the emotion or opinion that comes with a word. Think about the difference between if you hear cheap and affordable. They might both mean low price, but one sounds negative and the other one sounds positive. Now, let's look at something that is both powerful but also intuitive, distributional semantics. There's a famous quote from Perth, a linguistic in the 1950s. He said, "You shall know a word by the company it keeps." In other words, if two words show up in similar contexts, they probably mean something similar. Let's say the word bat often appears in sentences with words like flying, is, the, and the word bird also shows up with the same words. That's a clue. Maybe two words have something in common, in terms of meaning or whatsoever. This idea is the core of distributional semantics. We figure out what a word means by looking at the words around it. From this, we get something called a word embedding. That's just a way to turn a word into a vector of numbers. Those numbers represent the meaning of the word based on its context. If two words have similar meanings, their vectors will also be close to each other. And that's how models can tell that bird and bat are somehow related. At the very basic level, this can be done using a co-occurrence matrix, like the table actually shown here. You count how often each word appears next to each other. This gives us simple numerical features. It's simple, but it already gives us a very good starting point for comparing word embeddings. Now, let's take a look at one of the most important early breakthroughs in embeddings, word-to-vec. Word-to-vec is a method where we can train a very small or shallow neural network, and the goal is simple. We try to predict words either using their context, by predicting their context. There are two ways this can work. The first is called CBOW, which stands for continuous bag of words. In continuous bag of words, we take the surrounding words, like the two before and the two after, and then try to predict the word in the middle. So in this example that we have on the slide, we are feeding in the words at time steps. T-2, T-1, T+1, T+2. And then we're trying to guess the word at time T. The second option, not shown here, is also called skipgram. It flips the setup. We start with the center word, and then we try to guess the surrounding ones. But yeah, now here's the key point. Once we train this network, we throw away this output layer. What we keep are the weights. Those are the magic, the numbers inside the model. And those weights become our word embeddings. These weights capture what the network has learned about how those words are used. And that's how words get represented as vectors in word-to-vec. So far, we've talked about static word embeddings, like word-to-vec, where each word gets just one vector. But that's not enough. What if we had the word bank to mean something different in riverbank versus savings bank? That's where contextual embeddings come in. With contextual embeddings, the meaning of a word changes depending on the sentence around it. These embeddings are created using deeper neural networks. Currently, they're often built with the transformers. I hope you got enough into transformers within this lecture and also within NLP 1. So as you know, a popular example is BERT. So transformers take in full sentence, process it using layers of attention, which does not really just look at the word. They look at how it relates to every other word in the sentence. This gives us embeddings which are context-aware. The vector of the word bank in riverbank will be totally different from bank in money bank or bank account. So here's the main idea. In these modern worlds, the word embedding is not fixed. It's the output of the network depending on the sentence. And that's why we say contextual embeddings are neural network weights for a word in a specific context. So now, embeddings are not just a number for each word, they are smart. They understand meaning based on context. Now let's directly compare a static and contextual embeddings using an easy example. On the left here, we have static embeddings, like from word to vec, glove, or fast text. These models give one fixed vector per word, no matter where or how the word is used. So if we take the word bat, whether it's in bat flies by, the bat bites, or have you seen the bat, the vector stays exactly the same. Same number every time, as you see on the left. 3 arrows, same vector. But the language isn't that simple, right? In this example, bat clearly has different meanings. And that's where contextual embeddings On the right side, we use models like BERT, Elmo, DeBerta, whatsoever, right? These models look at the entire sentence. So the word bat gets a different vector in each sentence, shown by the 3 different vectors. Because its meaning actually changes with the context right now. And this is a huge step forward. It means the model isn't just memorizing words, right? It's actually understanding the usage of the words. You could take a second and think, what's another word you know that changes meaning depending on the context? Then you really start noticing how important these contextual embeddings are in the current research field. But maybe a question that you have on top of your mind right now is, why do we even know about those static embeddings, right? Aren't you saying contextual embeddings are so smart, cool, and they do everything around, and we don't have to know anything about static embeddings anymore? Actually, that's not the case. Let's compare static and contextual embeddings side by side to make sure that the differences are really clear. Static examples are simple. Each word has just one vector, no matter the sentence. These embeddings do not know anything about context, and they can't handle words with multiple meanings like, as we said, bad or light. Yet, an advantage is they are fast. They don't need a lot of data. You can train them quickly, even from scratch. Well, contextual embeddings are more powerful. Those models give you different vectors for the same words depending on its context. They don't just look at the word itself. They understand the full sentence. That means they can represent different meanings and capture how language actually works. But there is a cost. Training these models takes a lot of data, a lot of computing power. This is also why you see right now most of the contextual embeddings models are actually coming from the industry, because this is where there is a lot of data, there's a lot of computing power, there's a lot of money for this, you know? So we usually use pre-trained model like BERT and fine-tune them for our specific tasks in action. And finally, an important point, these models learn from their data, which means they can pick up biases. And because they are so complex, it's also harder to explain. But in short, contextual embeddings are smarter, but also more different to train, adopt, and understand. So, if you're building a model for, let's say, a very specific domain, legal documents, health, whatsoever, which type of embeddings would you choose and why? Now let's talk about something important that happens before even we get into embeddings, tokenization, especially for subwords. Modern language models do not always work on whole words. Instead, they often break words into subword units. One common method is called byte pair encoding, or BPE short. BPE works by merging the most frequent pairs of characters or subtokens again and again, until we get a fixed size vocabulary. But it sounds clever, right? And it is. But it also depends heavily on the training data. If a word does not appear often enough in the training set, it might get split into parts that do not really make sense. For example, the word photosynthesis may be broken into photo, syn, de, cis, which still can be useful, but something like COVID-19 could end up chopped into very confusing pieces if the model hasn't seen it enough. So while subword tokenization is powerful and helps deal with unknown or rare words, it's not perfect. It might split up very important domain-specific terms. So yeah, it's time to think. It's good to ask, are my most important terms being broken apart in a way that might hurt performance? Now let's talk about what happens when a word is split into subwords, or when we want to get embedding for something bigger, like a full sentence. This is where pooling comes in. Pooling is simply a way to combine multiple embeddings into one. One method uses a special token. For example, in BERT, we have this CLS token This stands for classification, and it's actually designed to hold a summary of the whole sentence. Another common way is to average the subword embeddings. So if a word is broken into 3 pieces, we take the average of these 3 vectors to get one single vector for the full word. If you're working in a specific domain like medicine, law, you might need to add new words, and in that case, you can either initialize them based on similar known words or again average the subword embeddings. Pooling does not just happen across tokens. It can also happen across layers. For example, we might take the last 4 layers of a transformer and average the embeddings. It's actually quite common in studies that look at how word meanings shift over time or across contexts. So pooling helps us go from many small pieces like subwords or model layers to one clear and useful representation. Let's now look at how contextual embeddings are trained. There are 2 big categories, the token level training and the sequence level training. First, with the token level training, this works at the level of characters, subwords, or single words. A single example is language modeling, where the model predicts the next word based on the words before it, like in GPT. And then in BERT, we have masked language modeling. Here, some words in the sentence are hidden or masked, and the model tries to guess them. Other related tasks include replaced token detection, where the model checks if a word has been swapped out, and whole word masking, which ensures the entire words are masked instead of just subwords. And there's also SBERT, for example, goes a step further and masks spans or chunks of text, then tries to predict the boundaries, which brings us to the sequence level training too. Now, we have the training tasks for sequence, like full sentences or even full documents too. Here what we care about is the meaning of longer text. One approach is cosine similarity, so training the model so that similar sentences have similar embeddings. Okay. A popular method about this is called contrastive learning, and this means the model learns by comparing. It pulls similar examples close together and pushes different ones apart. For that, we use techniques like triplet loss, SimCSE, and PromptBERT. They all rely on contrast, anchor positive and negative pairs. Another method, which is TSDAE, which has a fancy name, but in the end it just means like take a sentence, mess it up a bit, and then train a model to reconstruct it. So in short, we train contextual embeddings either by guessing missing pieces or by comparing full sentences to teach similarity. Let's now look at how SentenceBERT or SBERT is trained to produce high-quality sentence embeddings. On the left side, we see the cosine similarity loss setup. It works like this. We take 2 sentences, A, B, and feed each to a BERT model. Each BERT model gives us token-level embeddings, which we then combine using pooling to get one sentence vector. Let's call them right now U and V. Then we compute the cosine similarity between those 2 sentence vectors. The goal is to make those similarities high if 2 sentences are similar and low if they are not. Whereas this value ranges between -1 and 1, the loss function tries to match it to target similarity score, depending on how related the 2 sentences are. On the right side, we have triplet loss, which is a type of contrastive learning. Here we work with 3 sentences at once. An anchor sentence, the one we care about, a positive sentence, which is similar in meaning, and a negative sentence, which is different in meaning. So the idea is that we want the anchor and positive to be close together in the embedding space, and the negative to be further away. So the loss function, as you see here, compares these distances. If the negative is too close to the anchor, the model gets penalized. This helps the model learn what makes two sentences similar or different, not just based on keywords, but based on meanings. So whether we use cosine similarity or triplet loss, the goal is the same, is to train a model that turns full sentences into meaningful vectors, useful for search, clustering, classification, and many more tasks. So far, we've talked about general purpose models like BERT, but in practice, sometimes we want models that are more specialized. Let's take a look at a few directions where contextual embeddings have been extended or fine-tuned. Domain-specific models like BERTotweet for Twitter, SciBERT for scientific texts, PatentBERT or BioBERT for medical papers. Those models speak the language of their domain. Then there are language-specific models like Camembert for French, FinBERT for finance, TBERT for Tamil, IndoBERT for Indonesian. These are trained fully on one language or domain to perform better than multilingual models. On the other hand, we have multilingual models like MBERT, XLM Roberta, or multilingual SBERT. These can work with many languages at once and are great for cross-lingual tasks. Multimodals. So some models go beyond text, like SpeechBERT, Clip, or Blip. This can understand text and images, or even text and audio. For example, matching an Instagram caption to a photo. And finally, there are models that include structured knowledge, like NoBERT, which combines BERT with external sources like WordNet, Wikipedia, and so on. So in the end, depending on your task, language domain, or even data type, there is a probability, or there is probably a specialized embedding model that fits better than a plain vanilla BERT that you can use, experiment with, and so on. Let's now talk about how we can adopt the contextual embeddings to better suit our own use case or data. The first way is to continue training the model on more data, but data that comes from our specific domain. For example, if we're working with medical text, we can do continued pre-training on medical articles or research papers or whatsoever. The second option is to fine-tune the model on labeled data for a specific task, like semantic similarity or natural language inference, NLI. And this helps the model learn exactly what we want it to focus on. Another approach is instruction tuning, used in models like in Instructor. Here we don't just give the model a text, we also give it a task description. So for example, instead of just saying this is a product review, we add represent the review comment for classifying the emotion as positive or negative. This makes the embedding a bit more task aware. And finally, in some cases, we don't train anything at all. We just simply use the pre-trained model as is and try to get the best result with smart prompts or by adjusting the pooling strategy. So yeah, whether you're training, fine-tuning, or just reusing, there are many ways to make contextual embeddings fit your problem better. If I were you, I would have been asking one question right now. How do we actually compare embedding models? And that's where the Massive Text Embedding Benchmark, or MTEB, comes in. It's a large-scale benchmark designed to test how well embedding models perform across the different tasks. So it includes 8 different tasks, 56 datasets, 117 languages, so it's very broad. So what it tests, it looks mostly at sentence and paragraph level tasks like classification, clustering, and retrieval. And one thing to note is it does not test word-level tasks, so it's focused on use cases where full text understanding is needed. So here you can see a real snapshot where we just, I think, screenshotted a couple of days ago on the recent results. Models like Gemini Embeddings or Qwen, Mistral are compared based on how they do across those tasks. For example, zero-shot classification or by-text mining. This is the latest leaderboard. This helps the researchers and engineers choose the right model depending on where they care about performance, language, coverage, memory limits, and whatsoever. But of course, like all the benchmarks, no benchmark is perfect. MTEB has imbalances. Not every task is equally covered. Some languages are also underrepresented. So don't treat those scores as the final truth. Instead, use them to get a general idea of how capable a model is, and always test it on your own data if you can. So yeah, because there is no one-size-fits-all solution in embeddings. It's all about the task, the language, and your needs. So far, we've looked at how embeddings are built, how to train them, how we can adopt them. But now we move to something that is just as important, and even, in my opinion, a bit more interesting. So how do we analyze those embeddings? What kind of information is hiding inside these vectors? What do they really capture about language or even about the world? In this section, we actually will go ahead with exploring how to open up this black box and look at what these models have actually learned. And what can we do with that knowledge so far? So now that we know how to create and use those contextual embeddings, the next big question is, what's actually inside these vectors? What have the neural networks learned? These embeddings store a lot of information, not just about language like grammar or syntax, but also about the world itself. For example, they might learn that a doctor and hospital are related, or that ice is associated with cold, even if we never told the models those facts directly. But this also raises new questions. Could the model be encoding harmful patterns? Could it be learning biases from these data, like stereotypes or unfair associations? And beyond that, we want to know, what can we use those embeddings for? Can they help us detect trends, compare meanings, explore language shifts over time? So in the end, it's like understanding what's inside these embeddings helps us trust, improve, and responsibly use these powerful tools. So how do we actually analyze embeddings? We can just look at the numbers and understand them, right? We need tools to help us interpret what these vectors mean. Dimensionality reduction, for instance. Embeddings are high dimensions. Sometimes it's 768 or 1024 numbers long. But we can use techniques like PCA or TSNE to squeeze them down into 2D or 3D so that we can better visualize them. Once we reduce the dimensions, we can try clustering those embeddings. This helps us see if similar meanings naturally group together. For example, words about animals in one cluster and emotions in another cluster. Another technique is called probing. We train a simple classifier to predict a certain property from the embeddings, like part of speech, tense, or even if sentence is a question. If the classifier performs well, it means the information is probably stored in the embeddings, even if the model wasn't trained explicitly for that task. Finally, we can also take some inspiration from psychology and social sciences, using methods like association tests or semantic differences. This helps us ask, does the model think insect is unpleasant, or that certain names are associated with certain traits? And then we'll explore those methods in more details here. All of those tools give us different angles to understand what embeddings know, and also what they may be biased towards. Here we wanted to bring a real example of dimensionality reduction applied to sentence embeddings from BERT. So in this study by Shramovsky et al. In 2022, They utilized PCA, which reduces high dimensionality vectors down into just 2 in their example, so we can visualize them. So each dot here is a sentence, like help old people, steal time, become evil, or just pick your favorite from the slide. And they're just placed on the map based on their position in the BERT's embedding space. And look about what actually happens. You can draw a line between what BERT seems to think are morally good versus morally bad behaviors. Sentences like become better person and love my work falls on the right, closer to the do's, where kill people, lie to my wife, harm animals cluster on the don't side. And this shows us that even though we never taught BERT morality explicitly, it has picked up a sense of right and wrong from its training data, which is both amazing and a bit concerning, because it means models may be learning values, but we're just without us realizing it. So yeah, if you're building a chatbot or a decision support system, would you want to have it those values? Or how would you even check what values are included? These top 3 plots shows us something really nice. They tell us what kind of information is learned at each BERT layer. So if you look at the first one, the lexicon, how a word looks like. In the first plot, we look at surface level features like casing. Is it uppercase, suffixes like ing, ed, or whatsoever, or n-grams, the short sequence of characters. We see these features are very strong in the earlier layers, so around layer 1, 2, 3 out here, which means that BERT first learns about what words look like. Then the information fades, which is good, which makes space for deeper meanings later on. Then we go into morphology and semantics, which is what the word means. So in the second plot, B, we look at morphology and meaning. POS is part of speech. LIWC are psychological categories, like said words, for example. WordNet are semantic categories, like animal, emotion. And here we see a rise towards the middle and deeper layers. This means BERT is starting to understand what words are and how they relate to ideas. And then in C, how words connect in a sentence. The third plot is about grammar structures, how words are organized in a sentence. Things like chunking or predicting the first word in a phrase get captured best at deep layers, around layers 8 to 11. So early layers learn form, middle layers learn meaning, and deeper layers learn grammar. And that's how BERT builds its understanding of languages. Now let's actually take a look at the bottom word clouds. At the bottom, we see example of the kind of concepts BERT has organized. On the left, we have a cluster of ages, like 90 years old, 76, 75, 33, whatsoever. In the middle, we see descriptive adjectives like smartest, bravest, cutest. And on the right, we see place names, mostly German cities and reasons. So this shows how embeddings group related ideas together and how the structure grows deeper and more meaningful as you move through the layers. Once we have our embedding, like this vector here, we try to probe it for certain properties. We feed it into a probing classifier like shown out here, which can be a simple linear model or something more complex. And we train it to predict some property of interest, which could be part of speech tags, semantic roles, grammatical features like tense, numbers, or even biases or moral framings. If the classifier performs well, this suggests that this information was actually encoded in the embedding, and the probe is just extracting this one. This way, we're not training the model itself. We're just asking, hey, is this information already there? And this is often described as estimating the mutual information between the embeddings and a specific linguistic feature. So why is probing such a popular method to analyze embeddings? One big advantage is flexibility, so we can apply probing to any type of embeddings. We can probe for virtually any property like part of speech, sentence length, semantic roles, and even modal judgments like we saw earlier. But it comes with important caveats. First, there is an accuracy-complexity trade-off. If I use a very simple classifier and it does well, I can confidently say that the information was already present in the embeddings. But if I use a powerful neural network, maybe it is the classifier, not the embedding, that is learning the pattern. And second, that there might be some spurious correlations. So the classifier could pick on something that correlates with the target property, but isn't actually what we care about. So overall, designing a good probing task isn't really that trivial. It requires careful thoughts about what we're measuring and how we are interpreting the results. All right, let's step into the world of social psychology for a moment, because it actually has a lot to teach us about how to understand language models. So what you're looking at here is the classic implicit association test, or IAT, which was introduced by Greenwald in 1998. It's very simple. People are shown categories like flowers and pleasant on one side, and insects and unpleasant on the other. And then they are asked to classify a word like ant by pressing either the left or right key. In this setting, ant is more quickly associated with insects or unpleasant because those categories feel more intuitively linked to most people. Then in the second version, the categories are just flipped. So insects is now paired with pleasant, and suddenly people are slower to respond. Why? Because the combination does not really align with our internal biases, right? And the key idea in this is this. Our reaction time reveals the strength of associations in our mind, even if we are not consciously aware of them. So again, what does this have to do with embedding? We can apply a similar logic. If a language model embeds flower and pleasant close together in a vector space, that's kind of like a fast reaction time. It suggests that the model learned a similar association. This becomes a really powerful tool. We can test if a model implicitly encodes social biases, for example, whether certain genders are more closely associated with specific jobs. And just like in psychology, we don't need to ask the model directly. We just watch how it behaves under controlled tests. It's a nice way to probe the mind of a model using methods originally designed to probe the human mind. Now let's take that idea of associated testing and bring it into the world of embeddings. Instead of measuring human reaction times, we now look at distances between vectors in the vector space. Here we've projected word embeddings into two principal components, PC1 and PC2. Just like reducing dimensions with PCA, this lets us or helps us visualize relationships that would normally be hidden in a 768 dimensional space. We've got groups of words. On the top left, we have words like chaos, freedom, health, grouped under pleasant. Below them, words like aster, clover, categorized as flowers. On the right, we see caterpillar, flea, and ant under insects. And further down, we see abuse, crash, and filth under unpleasant. And here's the key point. Notice how flowers are spatially close to pleasant, and insects are closer to unpleasant. And this is how we read the mind of a model, by checking how similar concepts cluster in its internal world. It means, much like humans, the model has picked up on associations between flowers and good feelings, insects and bad ones, without ever being explicitly told that. This is powerful, but it's also potentially dangerous because it shows how models can learn and internalize associations, including also harmful or biased ones, from the data they are trained on. So associated tests, when transferred to embedding space, become a diagnostic lens. They let us ask, what kinds of implicit relationships has the model learned? And are they what, or did they learn what we want them to actually learn? Let's now look at how these associations are quantified with the WEAT, or the Word Embedding Association Test. This was introduced by Kaliskan et al. In 2017. The idea is simple, but really powerful. So we use cosine similarity to measure how closely two groups of words are associated in the embedded space. Here's how it works. We define two target sets. Let's say X, words like insects and flea. Y, words like flower, clover, and so on. And two attribute sets. A, pleasant, like health, freedom, cares. Unpleasant, words like abuse, filth, and crash. We then calculate the difference in how close each target set is to the attribute set. If one target group is systematically closer to pleasant and the other to unpleasant, this signals an implicit bias in the embeddings. And what did they find? That actually word embeddings contain human-like biases. So even if you think about morally neutral categories, like take, for example, insects versus flowers, those show skewed associations. And more worryingly, these biases extend also to race, gender, and more. For example, math terms like algebra were more closely associated with male names, and art-related words like poetry were more associated with female names, which was a breakthrough that showed even models trained without explicit labels on just large amount of text could learn and reflect the biases presented in the text. So WEAT helps us quantify bias, not just observe it, and that's a crucial step towards addressing fairness in AI. Now let's take the idea of bias testing into a step further. With CAAT, the Contextualized Embedding Association Test proposed by GUO in 2021. Unlike WEAT, which tests word-level embeddings, CAAT works with contextual embeddings, like those generated by BERT or GPT. That means the meaning of a word depends on the sentence it's in, just like in real language. So how does it work? It samples sentences from a reference corpus and compare how different concepts are associated in context, not just as standalone words. In this table, we are seeing how 4 different models, Elmo, BERT, GPT, and GPT-2, perform on several biased texts. Let's look at a few. In C1, flowers versus insects, and whether they are more associated with pleasant or unpleasant contexts. You will see strong associations in all models, though interestingly here, GPT-2 shows weaker effects, which could be due to its architecture or training data diversity. C3, the European American names versus the African American names. So this also with pleasant versus unpleasant. So this test investigates the racial bias, and notice how BERT and Elmo still show significant bias with high effect size D, while GPT and GPT-2 drop closer to neutral or even negative. C7, as we talked with math versus arts, with male versus female associations, again confirming gender bias in embeddings. And there's more, like mental versus physical illness in C9, instruments versus weapons, science versus arts, all show varying degrees of bias depending on the model and context. So what does this thing reveal? It reveals that bias isn't just baked into word embeddings, but also show up in the way the models contextualize language. It's an important diagnostic tool, not just to prove that the bias exists, but maybe to track where it comes from and even how to fix it. Before we jump into the modern embeddings, let's do a fast rewind a bit for 19 to 1952 to the work of Charles Osgood on semantic differentials. Osgood's idea was simple yet powerful. So let's measure the meaning of concepts by placing them along polar adjective scales, like good versus bad, active versus passive, and so on. So here's what he did. He took two groups of people and asked them how to rate a word, in this case, polite, on this opposite attribute: angular versus rounded, weak versus strong, gruff versus smooth, active versus passive, small versus large, and so on. You can see the results plotted here. Even though both groups were evaluating the same word polite, their mental representation of it differed completely across the polar dimensions. This method revealed that the meaning is not absolute. It's contextual and shaped by associations across multiple axes of interpretation. This concept is foundational for what we now call polar embeddings, and that's what you see in the title, where words are projected into vector spaces along defined semantic axes. So instead of just using dense embeddings with 768 dimensions we do not fully interpret, we can now explicitly measure where a word lies on, let's say, honest, dishonest, liberal, conservative scale, much like Osgood's early work. And this is the inspiration behind polarity as a lens to understand and structure language in embeddings. Now let's move from the inspiration to an actual implementation. The polar framework introduced by Matthew et al. In 2020. The idea is also simple but powerful. So use polar opposites like strong, weak, honest, corrupt to define an interpretable subspace within the high-dimensional world embedding space. So step 1, define the polar subspace. We begin by collecting a pair of antonyms, shown here as like PZ, P minus Z, P2Z, P2 minus Z, and so on and so forth up to N. Each pair defines here a semantic axis. For example, the vector from weak to strong, from honest to corrupt, and so on. By combining all of N of these, we get a matrix of directions that forms our polar embedding space. Now let's say we want to understand how a word like leader sits within these semantic dimensions. Here, direction transpose EV equal WV tells us that we are projecting the original word vector WV, which is in the full embedding space, onto the new interpretable axis defined by direction transpose, which is the transpose of the matrix of the polar directions, which gives us EV, the word's position in the polar space. Essentially, how much leader aligns with each semantic axis. The second equation just arranges the same logic algebraically, so it let us go from polar space to the original if needed by saying that the word's position in the polar space, EV, equal the inverse of the transpose of the matrix of polar direction multiplied by the original word vector. So overall, this framework let us take black box word embeddings and reframe them in terms of intuitive, human-defined contrasts that incredibly helpful for interpretability, especially in applications where we want to track moral, emotional, political, and whatever other connotations in the language. Now let's move to a cool extension of the polar framework. It's called Sense Polar and was proposed by Engler et al. In 2022. So the key idea here is to go one level deeper than words and work with word senses instead. So instead of just saying bank as a word, Sense Polar tries to distinguish if we mean bank as in river bank or money bank. And to do that, it uses sense embeddings, meaning each word is split into its specific meaning. using dictionaries like WordNet. This means we can project sense-aware vectors into a polar space using example sentences that clearly describe each meaning. So you can see an example here on the right for the sentence music is life, for example. SensePolar projects this into a space of semantic contrasts like musical versus unmusical, harmonic versus non-harmonic, experience versus inexperience. Each sense is plotted along the polar axes based on how it fits in the context. For example, the word music aligns strongly with musical, harmonical, but not with unmusical, right? And that makes sense. At the bottom, you can see a performance comparison which shows that even after this transformation, the results on question answering benchmarks like Squad and Co. are almost the same or slightly better. So the key takeaway is we get interpretability without sacrificing model performance. And this makes SensePolar a promising tool for analyzing meaning in a contextualized models like BERT. We've now seen how polar embeddings allow us to map meaning onto interpretable axes like good, bad, strong, weak. But what if we want to scale this idea up to more abstract or social concepts? That's what this slide is about. Extending polar embeddings to broader semantic dimensions. So take the example on the left. Researchers like Fraser in 2021 looked at stereotypes dimensions, things like warmth or competence. Instead of a single word pair, we now define each pole using entire word lists. For warmth, the high warmth side could include friendly, warm, and pleasant, and the low warmth side could be cold, repellent, and disliked. We can then project concepts or occupations into this polar space, as you see on the right. The y-axis is warmth, while the x-axis is competence. We're visualizing different groups or occupations in this space. For instance, nurses appear as high in warmth, but moderate in competence. Managers are seen competent, but low in warmth. And for instance, take a look at schoolboys, schoolgirls, or grandfathers and how they land differently across these two axes. So this helps validate known stereotypes or challenge them using embeddings. But this approach isn't without limitations, actually. So you really need opposites, which isn't always obvious for abstract traits. You often rely on dictionaries or curated lists, which again introduces human bias. And most importantly, you need high-quality context example, because bad examples could really distort the projection and reinforce harmful assumption. So polar embeddings can scale, but they must be handled with care. So let's wrap up this part with some of the good opportunities that come from analyzing contextual embeddings. So first, we get a glimpse into what LLMs have actually learned. So embeddings let us peek inside the model and check if it captures real-word associations, or if it captures maybe strange ones we did not really expect. So it's a reality check, not of the output, but of the underlying mental map of the model. Second, we can use the embeddings for bias measurement. For example, we can test whether doctor is closer to he than she, or similar examples. But there is a catch. Bias in the embedding space does not always translate to bias in downstream tasks like classification or summarization. So we should always validate both of them. Third, we can try to reduce bias with techniques like debiasing projections, for instance. Again, with the same caveat, fixing embeddings does not always fix behavior. Fourth, there is a potential to optimize embedding space. That means making them more interpretable, compact, task-specific. For instance, learning better access for analogies or clustering. The final one is that it opens the door for studying digital society through language, which is really interesting. I hope you see it the same by now. So embeddings let us quantify stereotypes, track cultural shifts, or study representations of social groups across time and corpora. So even though they are just vectors, embeddings are really powerful tools, and we're only scratching the surface of what they can tell us. However, it's really important to be realistic about the challenges involved in analyzing them. So first, the structure of the embeddings is inherently complex, and we have to admit that one. They live in a high-dimensional space and are distributed across layers in a model like BERT or GPT, which makes it hard to say which representation we should actually analyze. Is this the last layer, the average of all, coming with something else? Second, embeddings suffer from anisotropy. This means that the vectors are not evenly distributed, and some rogue dimensions may dominate the space. So, your cosine similarities might be influenced by weird artifacts rather than genuine semantic closeness. A third one is that everything is entangled. So embeddings encode not just meaning, but also syntax, factual associations, and even token positions. So when we say two words are close, are we talking about similar meanings, similar grammar, or just co-occurrence? And finally, context makes everything even messier. So the same word can have completely different embeddings depending on the context. So we face a critical question. Which context example should we use to measure bias or similarity? So while embedding analysis is powerful, it's also messy. And we need to be really thoughtful in how to design those studies and also cautious in how we interpret them. Now that we have explored how embeddings represent meanings, let's turn to the applications that we can apply embeddings to words, and one of their most exciting applications, which is topic modeling. So traditional topic models like LDA assume a bag of word representation with no context, no order, and very limited detail. But then with the world of embeddings, especially contextual embeddings from models like BERT, we can now represent each document or even each sentence as a dense vector that captures the semantic meaning. And this allows us to cluster similar text together, or detect the emerging topics, or explore hidden themes, all without relying on predefined keywords. This gets really interesting in a lot of research directions. For instance, what I'm personally doing in the automated journalism. So this helps more classifying or clustering the different conversations from social media into different cluster of topics or social groups, or identifying the emerging hot topics as we talk. In the next slides, we'll look at how this embedding-based topic modeling works and why it can be more flexible, more robust, and often more interpretable than classical approaches. So pre-trained contextual embeddings like those from BERT or GPT are really versatile. Here are some of the most common applications. For instance, semantic search, where you retrieve information based on meaning, not just like keywords matching or fuzzy matching, of like, hey, if you see this keyword, just bring it. But it's just like getting the semantic understanding and then performing semantic search accordingly. We're also talking about RAG, which is getting super popular right now, or retrieval augmented generation applications, which is covered during the Advanced NLP lecture. Embeddings can also help visualize and explore relationships in data through exploratory data analysis, EDA. It also helps studying meaning and how it shifts over time or across contexts. and most importantly for today's lecture, topic modeling. So even though contextual embeddings are powerful, yet again, have to say that static embeddings like WEAT or GLOVE are still widely used. The reason is that they are fast to train from scratch, and since they don't rely on massive pre-trained corpora, there is no inherited bias from external data. And they're also useful for studying dataset-specific bias, not just the bias introduced by a large model. So both static and contextual embeddings have their place, depending on the use case. Let's begin our deep dive into topic modeling. So topic modeling is all about discovering abstract themes or hidden structures in a collection of documents automatically. So as you see, you feed in a bunch of documents, shown on the left, into a topic model. This could be something like LDA, NMF, or a modern embedding-based approach, and the model learns to group together frequent co-occurring terms. And what we get out are topics. So each topic is represented by a cluster of words that tend to appear together. Like for example, one topic might include words like bat, bird, dragonfly, mosquito, all related to flying creatures. And another one might be fly, flying, air, wind, which focuses on the actual act of flying. And yet another could be rain, sun, thunder, wind, which clearly linked to weather. Those word groups give us insights into the latent themes present in the text corpus without requiring prior label or supervision. Before we had neural topic models, one of the most foundational approaches to topic modeling was the latent Dirichlet allocation, or LDA. This was introduced by Bley et al. In 2003. So LDA is a generative probabilistic model, which means it tries to describe how documents could have been generated, assuming that each document is a mixture of topics, and each topic is distribution over words. Those two assumptions are really important as we go further. So let's walk through this graphical model diagram step by step. So alpha, this is the parameter of the Dirichlet distribution that governs how topics are mixed within a document. So it tells us how likely is a document to be about multiple topics versus just one. And then we go into theta. For each document I, we sample a topic distribution theta sub I from the Dirichlet distribution defined by our alpha. So think of it as saying this document is 70% about politics and 30% about sports. Then we go into Z, which is the topic assignment. So for each word J in document I, we pick a topic Zij. This tells us how, which topic the word will be drawn from. So now we're saying the fourth word in the document is coming from the sports topic. And then we go into beta, which is another Dirichlet prior, but this time over words in a topic. So this governs how likely words are under each topic. And then we go to W, which is the word generation. So given the chosen topic Z sub ij, we then sample the actual word wij from the topic's word distribution phi Zij. So this gives us final word or the final word we see in the document. So let's recap again the notation. M is the number of documents. N sub I is the number of words in document I. Alpha is the Dirichlet prior for topic mixtures per document. Beta is the Dirichlet prior for word distribution per topic. Theta I is the topic distribution for document I. Phi sub k is the word distribution for topic k. And then Zij is the topic chosen for the jth word in the document I, whereas W sub ij is the actual word. So to summarize, LDA assumes that documents are probabilistic mixtures of topics, and that each topic is probabilistic distribution over words. The model learns both the hidden topics and how each document mixes them. This generative process let us work backwards. So given only the words in the documents, we try to infer what the topics are and how are they distributed. And this approach paved the way for all modern topic modeling techniques, in my opinion. If you're actually good with LDA till now, feel free to skip this one. However, I also like to give another analogy with cooking, for example, to understand the LDA idea intuitively. So imagine we are in the kitchen. Each document is like a dish you are preparing. Each topic is like a recipe or a cuisine, let's say Italian, Mexican, or Japanese. Each word is an ingredient in the dish, like garlic, chili, or soy sauce. So imagine the following process. You start with a recipe book. This is your topic distribution. Each dish will randomly mix several recipes. So one dish might be 70% Italian and 30% Mexican. I would have loved to say think about a Hawaiian pizza, but I'm not sure how politically correct is that. For each ingredient, like a word in the dish, you roll a dice to decide which recipe it should come from. Then, from that recipe's ingredient list, which is your topic's word distribution, you randomly pick an ingredient. So one dish might end up with mostly pasta from the Italian topic and a little bit of chili from the Mexican topic, and so on. So the clever part here is when we only see the final dishes, the documents, LDA helps us work backward. So it tries to guess which recipes were used and what ingredients belong to each recipe. So in real NLP terms now, documents are made up of words, topics are hidden, and LDA helps us uncover those hidden topic recipes and how they are mixed into each document. Let's now move from the classical topic modeling like LDA to neural topic modeling using variational autoencoders or VAEs. This is a method proposed by Miao et al. In 2017. And what's happening is that, as you see here, the process begins with the document represented as a vector X. Then it goes to the green blocks, the encoder. The encoder is a neural network that learns how to compress the document into a hidden latent space. So it estimates a mean and a variance for the latent distribution. From this, a latent variable R is sampled using the reparameterization trick, whereas R is equal to mu plus sigma, and multiplies by E. And E here is actually a random noise vector which ensures the differentiability. Then the latent variable R is transformed into a topic distribution vector theta, which represents how likely the document belong to each topic. Which brings us to taking the topic distribution in the decoding manner and a matrix beta which contains word distributions per topic, and then reconstruct the original document X. So the goal is just like an autoencoder. The input and output X should match. This happens by minimizing the difference between input and output while we learn meaningful latent topics through theta and beta. So let's get an example again like the LDA and say the document is a bag full of groceries, X. Encoder says, this bag seems to be 60% Italian cuisine and 40% vegetarian. The latent code R reflects that. From that, we generate a topic mixture theta, and the decoder then says, based on the mixture and what I know about cuisines from beta, let me try to reconstruct this original bag again. And if the reconstruction is close enough, the model has captured meaningful topic mixtures. Now let's move to a modern flexible approach to topic modeling, which is BERTopic, proposed by Groh, endorsed in 2022. So key point to know about BERTopic is that it's modular. It means that it's built from rather independent components, each doing a specific job, which I personally would like to refer to it more as a framework, which gives us lots of flexibility in adapting to different use cases. So let me walk you through the full pipeline bottom to top. We start by SBERT or sentence BERT. This takes our raw documents and turns each one into a dense numerical embedding. So each document is now a vector that captures its meaning and semantic content. But how about the dimensions now? Those embeddings are really highly dimensional, maybe 768 dimensions. Those are actually hard to work with directly. So next, we apply dimensionality reduction technique, UMAP here. UMAP flattens this high dimensional space into a lower dimensional one, usually around 5 to 15 dimensions while preserving the structure. And this helps us very much with visualizing and clustering the data more effectively. With those reduced embeddings, we then use HDB scan for clustering. And HDB scan is a great choice here because it's density-based, which means it groups similar points together, but leaves out noisy or isolated data. So if a document does not really belong to any of the clusters, we wouldn't force it into one, which makes it more realistic. But we're going to talk about what could be cons of this in a bit. But now, since we have grouped the document into clusters, we need to figure out what each cluster is about. For that, we return to the raw document and tokenize them using a count vectorizer, which turns each document into a bag of words representation. This is the tricky part. The important step is the class-based term frequency inverse document frequency. So instead of computing TF-IDF across individual documents, it treats each cluster as a single document and then calculates TF-IDF to find the most distinctive words for that topic. And this is how we get the meaningful topic keywords. At the very top of the stack, there is an optional fine-tuning step of the document embeddings. And this is helpful if you really are working in a specific domain, like legal, scientific, or medical, where pre-trained embeddings may miss important domain-specific meanings. So to recap, BERTopic goes from document embeddings to dimensionality reduction to clustering, keyword extraction, optional fine-tuning, which makes it one of the most popular topic modeling methods today, since it blends powerful transformer-based semantics with the interpretability of classical topic models. Now that we've seen the basic BERTopic pipeline, let's take a closer look on how modular this really is and why this is so powerful. So each block in the pipeline offers multiple plug-and-play components. Think of it more like Lego bricks. So we can swap parts depending on our needs, domain, or maybe computational budgets. So let's start by embeddings, the bottom layer. This transforms our raw text into dense vectors, right? The default is SBERT, but we can also use SimCSE or any model from the Hugging Face library depending on language covering and model performance and also our preferences. Next, to make the data more manageable, we said we apply dimensionality reduction, and the most common choice here is UMAP, but PCA and SVDs are also available, especially useful if you want a linear method or a faster runtime. Then we go ahead and cluster documents based on their reduced embeddings. So again, HDB scan is used because it actually doesn't require you to predefine the number of clusters, which is a very good advantage. But if you prefer traditional methods, if you, for instance, want to use k-means and you already applied your elbow method, you know which exact k you want to approach, or you want to use BERT, those are viable alternatives. And it also depends on the dataset shape, scale, and how you explored the dataset and your dataset knowledge, also domain knowledge in there. Then with the tokenizer, we said once the documents are clustered, we tokenize the texts into those clusters. Default is count vectorizer, but Chinese, for instance, you can use GBA for. And POS-based tokenizer can also help filter for nouns and proper terms to improve the topic interpretability. Then for the weighting schemes, for topic keyword extraction, we calculate scores for each word in a cluster, where we said our method is the CTF-IDF, but we can extend it with maybe BM25 or apply normalization for more fine-grained results. This step determines which words best describe each topic. And then for the representation tuning, you can use models like Llama, MMR, you can use also ChatGPT, you can use... those techniques help refine or re-rank topic terms to improve coherence or reduce redundancy. So as you see, BERTopic isn't one fixed method. We said it's a highly customizable framework where each step can be adopted to fit your language task or even the data constraints. So this makes it extremely flexible and suitable for real-world production use cases. To wrap up our discussion of BERTopic, let's consider both the strengths and the trade-off that comes with it. So, yeah, being on the good side, starting first with the advantages. So, flexibility is one of the biggest strengths As we saw earlier, each module in the pipeline is replaceable or interchangeable, so it's easy to adapt to different use cases or data sets. It also supports dynamic, hierarchical, multimodal, multilingual modeling all out of the box, which is really very rare in traditional topic modeling tools. And because it's built on LLM embeddings, it naturally improves over time as better sentence models are released, or even better approach over the Lego building blocks. And with HDB scan, we don't need to predefine the number of topics. As we said, it learns the number of clusters from the data itself. But now for the important caveats to be aware of. By default, each document gets one topic. And that might be a bit too simplistic for multi-topic texts like news article, scientific papers, also for the social media text. HDB scan can label many points as outliers. We said that we said that a couple of slides ago, right? So what this leads to is that it leads to those points being excluded from the topic assignment. And this can affect your coverage. There can be also a disconnect between clustering and topic labels. For example, a cluster may be very well performed in the embedding space, but the top keywords from the CTF-IDF step may not be fully coherent. You see it actually in action. Finally, while modularity is great, too much flexibility can be misused. So overfitting topics to expected labels or cherry-picking configurations for nice-looking results. So, as always, BERTopic gives you power, flexibility. With great power comes great responsibilities, but it also requires thoughtful validation and transparency when applied to research or production. That brings us here to a list of references we used while preparing those slides, and those slides are actually adopted from the slides from Caroline from last year Advanced NLP course. So a study approach would be minimal, work with the slides. Standard is the minimal approach plus checking out BERTopic best practices, and also like read a bit about BERTopic. It's really an interesting topic. In-depth, standard approach and scheme references for 6 and 7. Well, if you are still holding up till here, thank you very much for your attention. I hope we covered some interesting topics for you, and see you next time.